Hello guys, welcome back. Today we're going to be doing lesson 3.2 complex numbers, and today is really the day where we begin doing curriculum from the Algebra 2 curriculum. Up until now we've basically been reviewing Algebra 1, so everything we've seen you've seen before, everything we've seen in class so far. This is the first time that we're probably going to do stuff that you haven't seen, and that's okay. But it is essential, and it is really important that you pay attention and that you make sure that you understand what we're going to cover today. Alright, so in the last lesson and previously, if you came across a problem, let's say x squared plus 4 equals 0, and you were asked, excuse me, still have the really bad cold, and you were asked to solve this for x, right? What you would do would be subtract 4 from both sides, and you would get x squared equals negative 4. At that point you would take the square root of both sides, so x equals plus or minus the square root of negative 4. But at this point we would say, well, we can't do the square root of a negative 4, that's not a real number, which is true, and we would say no real solution. So this is what you would do up until today. If you came across this in a problem, you would stop right there and say, can't do that. We can't take the square root of a negative. And so we would have to stop solving our problem and just leave it alone. And that's exactly what happened to mathematicians back in the 1600s. They were solving these quadratics, and they'd get to a point where it's like, we can't do anymore because we're trying to take the square root of a negative, and there's nothing that is true that would make that true. So because they were not able to solve a lot of problems, the mathematicians decided, hey, let's come up with this imaginary number, one that we are creating, that has this particular property. The imaginary number is called little I. It looks like a variable, but it isn't. It's actually a number. And the value of that little I is going to be the square root of a negative 1. So it follows that if this is true, if I equals negative 1, then I equals square root of negative 1, then I squared equals negative 1. Okay? So this imaginary number, that again, they started playing with it around the 1600s, and then much, much, much later, I think it was Euler, I can't remember the other mathematician, they went ahead and made all of the created all of the different ways that we could use these imaginary numbers, how to add, subtract, multiply, and divide them, and really kind of gave us rules for how to deal with these imaginary numbers. And there were a lot of mathematicians along the way between the 16th century and the 18th and 19th centuries, probably up to the 19th century. So again, imaginary numbers have been around a while, and they help us solve problems that otherwise would be unsolvable. Okay? So now that we have this situation where little I equals the square root of negative 1, or this particular little I whose value when you square it is negative 1, we're able to do a lot of problems. We can find, for example, the square root of these numbers here. So find the square root of each number. We have the square root of a negative 25. Now right now you know how to do, for example, the square root of 25. Square root of 25 is 5. Technically it's plus or minus 5, right? Because negative 5 squared is also 25. But we'll just look at the positive root right now, which is 5. Now the square root of negative 25, we have to break apart into two parts. We have to break it into the product of the square root of negative 1 and the square root of 25. Okay? So we are pulling this negative 1 out. I'm going to call pulling the I out. Get it? The I? Yeah, see the little I there? There's the I. So you want to pull the I out first. Excuse me. Sorry again. So the square root of negative 1 by definition is I. And we're left with the square root of 25, which we know is 5. So we're left with I times 5. Normally we don't write it like that. We write 5I. That is the convention, to write the number here and then the little I after it. Okay? So the square root of negative 25 is going to be 5I. Technically it's really plus or minus 5I, but right now for us, for this minute, let's just use the positive root. Okay, let's take a look at B. Square root of negative 72. All right, once again, let's compare it to the square root of 72. If we had the square root of 72, we would pull out the biggest factor that's a perfect square, which happens to be 36, and 36 times 2 is 72. Square root of 36 is 6, 6 square root of 2. All right, now we're going to do this guy. Now in this guy, we have to break it up into 3 products, because the first thing is, you guessed it, take the I out. So we're going to pull out the negative 1, and then we're left with a positive 72. So that's going to be 36 times 2. The square root of negative 1, that is I. Square root of 36, that is 6. And again, the order that we write this is important. Sorry, this is not negative I, this is I. The order that we write this is important. This would be 6I square root of 2. It's just convention to write the number, then the I, and then the square root of whatever is left over. It's just easier to say 6I square root of 2 than I 6 square root of 2 or anything crazy, or square root of 2 I 6. This is just easier to say, and it is the format that we normally use. Okay? Let's take a look at C. Here we have negative 5 times the square root of negative 9. So let's do it when it's a positive 9, because we know how to handle that. So we take the square root of 9, which is 3, and then we multiply it by negative 5, and we get negative 15. Now with these, we're going to have to change this a little. We still have the negative 5, which doesn't go anywhere, but then this is going to break up into negative 1 and 9. Again, remember, take the I out, right? Take the I out. Pull that out first. So we have negative 5I, and then the square root of 9 is 3. So 3 times negative 5, that's going to be negative 15I. Okay? So this little I, these are called imaginary numbers. But now we're going to take a look at a complex number. A complex number written in standard form looks like this: A plus BI. This A is the real number part. And we're familiar with real numbers. That's what we've been dealing with all our lives. And then this BI is the imaginary number part. Okay? So let's talk a little bit more about complex numbers. Every number that has ever been can be written as a complex number. We're going to do a little bit of a graphic here. I'm going to create this big box, and in this box are all the numbers that have ever been, and these are your complex numbers, and they are of the form a plus bi. Now within this box is another box that's divided into two. Over here we have our real numbers, which we are very familiar with. And our real numbers are things like -1 or 5/3 or pi or square root of 2. All of these are our real numbers. And then over here we're going to have our imaginary numbers. Okay? And those are going to look like 2 plus 3i, 9 minus 5i. Now please note, this is not an expression. This is actually a number. It's the number 2 plus 3i. It all goes together. It is one number, just like the number, the fraction 5/3 is 5/3. It is just one value. It's not an algebraic expression. Okay? Now within these imaginary numbers we have what are called pure imaginary. And pure imaginary numbers look like this, except they don't have the real part. So a pure imaginary number would be something like -4i or 6i. All right? So let's recap this. Real numbers look like this. And if you were to write real numbers as complex numbers, it's really easy. This -1 would be -1 plus 0i, because there's no complex part, there's no imaginary part. 5/3 would be written as 5/3 plus 0i. Pi would be written as pi plus 0i, and so on. The 0i term, this bi term, would be 0 for real numbers. For imaginary numbers, you have an a and a b, an a and a b, an a and a b. And for pure imaginary numbers, your a is not there, so it's going to be 0. Excuse me. So the number -4i written as a complex number would be 0 minus 4i. And over here 6i would be written as 0 plus 6i, because the a's are 0. Here the b's are 0. Here neither one can be 0. Okay? So that lets us write every number we have ever worked with as a complex number, all the numbers. Again, we've only dealt with these in the past. These are the new guys. All right, let's move on to example 2. If I tell you that two complex numbers are equal, this is what I mean. All right, equality of two complex numbers. If I have the complex number 2x plus 7i, and I have the complex number 10 plus yi, and I tell you that they are equal, what that means is that this part, this real part, 2x, must be equal to the real part of the other complex number, which is 10. And that also tells me that 7i must be equal to yi. Okay, the two imaginary parts must be equal to each other. So now we can easily solve for the variables. We can solve for x here, dividing both sides by 2. So x is 5. And here we can divide both sides by I. Oh, I should have made this negative. Sorry, in my notes, this was a negative. So that's a negative. Just want to make sure it looks like the notes that you'll see in Schoology. Divide by I. So y is -7. And that makes perfect sense. If I put a 5 here for x, 2 times 5 is 10. And if y is -7, this would be 10 minus 7i, which is exactly the minus 7i that we want. So once again, if you have two complex numbers that are set to be equal to each other, we set the real parts equal to each other. Oops, sorry about that. And we set the imaginary parts equal to each other. Sorry. Gotta figure out why this thing is not lighting up the way it should. Alright, I'll figure it out eventually. Okay, so now that we know what imaginary numbers are, and now that we know what complex numbers look like, that they have a real part and they have an imaginary part, now we got to figure out how to perform basic arithmetic operations on them. So the 4 basic arithmetic operations are addition, subtraction, multiplication, and division. So let's start with addition because that's usually the easiest. And this is example 3. So if I am adding the complex number 8 minus I to the complex number 5 plus 4i, notice there's a plus sign between the two complex numbers, so this is an addition problem. The way we do this is really easy. We add the real parts together. So this is real and this is real. 8 plus 5, that's 13. And then we add the imaginary parts together. So we have a -1 plus 4, that's going to give me positive 3i. At this point, when we do addition, subtraction, multiplication, division, we are going to treat the little I like if it was a variable. It is not a variable, but we're going to treat it like a variable when we add, subtract, multiply, and divide. So for now, pretend it's like an x value, like it's minus x plus 4x. That's going to give you 3x, but in this case, it's 3i. So again, even though I is not a variable, this is an actual number, the entire thing is a number, we're going to treat it like if it was a variable. So let's do subtraction. Subtraction, we have 7 minus 6i, that is the entire number, minus 3 minus 6i. This is another number, okay? But we're going to treat it like a variable. So if you saw this, and instead of an I, this was an x, what you would do is you would distribute this -1, and that's exactly what you're going to do. So this becomes 7 minus 6i. Negative times 3 is -3. -1 times -6i is positive 6i. Notice we lose the parentheses at this point. We are just going to combine the real numbers together. So 7 minus 3, that is 4. And look what happens here. -6i plus 6i, that's just 0i. So this is just 4. There's really no need to write this unless you wanted to, but really no need. So this is a situation where you have two complex numbers, and when you subtract them, you're actually getting a real number, which is kind of cool. So we're crossing the barrier here. We have two imaginary numbers that when you subtract, you actually get a real number. Okay? And we'll be seeing a lot of this, especially with division. All right, let's take a look at multiplying these guys. So, example 4. Multiplying. Let's say we have 4i times negative 6 plus I. So here I have a pure imaginary number times a complex number. You're going to treat the i's as if they were variables. So you're going to multiply this by this, you're going to distribute, and then distribute it with that. So 4i times negative 6 is negative 24i. 4i times I is 4i squared. Now, one thing that you do need to realize whenever you're dealing with these imaginary numbers, whenever you see an I squared, remember what its value is given as. Remember, by definition, little I is equal to the square root of negative 1, which implies that I squared equals negative 1. So whenever you see an I squared, you must simplify it by putting a negative 1 in its place. And 4 times negative 1, that's negative 4. So negative 24i minus 4. Now normally when we write a complex number, this is a complex number, we put the real part first. So let's flip it around. Negative 4 minus 24i. And we put the imaginary part second. So real number, imaginary. Okay, let's take a look at another multiplication one. I think I can fit one over here. We have 9 minus 2i times negative 4 plus 7i. These are two complex numbers. Here you had one complex and one pure imaginary. Here you have two complex numbers that you're multiplying together. And again, we're going to follow the rules of algebra, pretending that this is a variable. We're going to use the FOIL method to multiply these like if they were binomials. Okay? So first is going to be 9 times negative 4. That's negative 36. Then we have outer, which is 9 times 7i. That's going to be 63i. Inner is going to be negative 4 times negative 2. That's positive 8i. And negative 2i times 7i, that's going to be negative 14i squared. All right, time to simplify. These two guys here are like terms, so we are going to add them together. That's going to give us 71i. And this I squared must be replaced with a negative 1. So negative 1 times negative 14 is positive 14. Finally, the real parts have to be added together. So negative 36 and 14, that's going to be negative 22. And then your imaginary part goes second. Okay? Now we're going to talk about a pair of complex numbers. These are two complex numbers. We're going to talk about a special pair of complex numbers. I'm sorry, I'm having such an issue with this camera. This lighting is driving me crazy. There's a special pair of complex numbers called complex conjugates. And complex conjugates look like this. For example, if I have the complex number 3 plus 2i, its complex conjugate has the same real part, 3, has the same imaginary part, and one is positive and one is negative. These two are complex conjugates. So 3 plus 2i and 3 minus 2i, they are complex conjugates. Negative 5 minus 6i and negative 5 plus 6i. They are complex conjugates. Again, the A stays the same, the B stays the same. What changes is the sign between them. What is very cool about these complex conjugates is that when you multiply them together, the imaginary part disappears. Oh, you think I'm kidding? Let's take a look. Let's multiply 3 plus 2i times 3 minus 2i. We know how to do this using FOIL. So 3 times 3, that's going to be 9. This is going to be minus 6i. This is going to give me positive 6i minus 4i squared. Look at this right there. Negative 6i plus 6i, that's going to go to 0. It's always going to happen with complex conjugates. And this I squared is going to go to negative 1. And negative 1 times negative 4 is a positive 4. So you're going to be left with 9 plus 4, which is nothing more than 13. So look how beautiful this is. Two complex numbers, multiply them together, and you're getting a real number out of it. All the imaginary stuff disappears. Now, if I wanted to generalize this, I would say a plus bi, any a plus any b times I, and you multiply that by a minus bi, you're going to get, again using FOIL, a squared minus abi plus abi minus b squared I squared. Once again, these two guys go to 0. The I squared becomes a negative 1. Negative 1 times a negative b squared is a positive b squared. So you are left with just a squared plus b squared. And if you don't believe me, this is a. What's 3 squared? That's 9. This is b, which is 2. 2 squared is 4. And 9 plus 4 is 13. And this is just the generalization for any a or b of what you just saw up there. So that, guys, is pretty cool. Now, why do we need these? We need them so that we can do division. Okay? So example 5. Division. Let's say I have 4 plus 3i, and I am dividing it by 2 minus I. Now, one of the things about imaginary numbers is that we cannot have them in the denominator of a fraction. It's horrible. You can't do it. Just like normally we can't do 3 over the square root of 2. I always tell you, no, get rid of the square roots. We can't have them in the denominator, and you have to rationalize the denominator, and you get something like this. Yeah? Well, here we cannot have an I in the denominator. We have to clear it out. And the way we're going to do it is, you guessed, we're going to use its complex conjugate. So you're going to get the complex conjugate of the denominator, and you're going to multiply by that complex conjugate over itself. And now we're going to watch the magic. So in the denominator, you're going to have 2 times 2, which is 4. Again, the outer is plus 2i, inner minus 2i, and then minus I squared. The numerator, we're going to FOIL also. We're going to get 8 plus 4i plus 6i plus 3i squared. All right. In the numerator, these two guys become 10i. And this I squared, remember, is negative 3. I'm sorry, negative 1. Negative 1 times 3, that's going to be negative 3. So in the numerator, we have 8 minus 3, which is 5, plus 10i. And then in the denominator, these two guys are going to go, which they always do when you're multiplying by a complex conjugate. And I squared is negative 1. Negative 1 times a negative, that's going to be positive 1. So in the denominator, I have 4 plus 1. This is going to give me 5 plus 10i over 5. And we can simplify that. 5 over 5 plus 10 over 5i. 5 over 5 is just 1. 10 divided by 5 is 2. So this is your final answer, and it is the answer of when you divide these two guys, you're going to get this complex number as an answer. Okay? Let me try and find another sheet of paper. Just a second. Okay, so let's do another example. Well, actually, let's do some quadratic equations. So remember, up until now, when we were doing a quadratic equation and we were solving for x, if we got the square root of something that was negative, we would have to stop. But no more, friends. Now we are able to move on. This lighting is horrible. Oh my gosh. I don't think my hands look that awful in the real light. Solving, but maybe, I don't know, quadratic. This was not the situation a few videos ago, so something's going on. All right, solving quadratic equations. So I think I already did this one, but we're going to do it anyway. If we had x squared plus 4 equals 0, and I ask you to solve for x, you're going to subtract 4 from both sides. You're going to get x squared equals negative 4. You're going to take the square root of both sides, so x equals plus or minus. Now you're going to pull the I out, all right, which is the square root of negative 1, and the square root of 4. The square root of negative 1 is I, and the square root of 4 is 2. So x equals plus or minus 2i. Let's take a look at B. Let's say we have 2x squared minus 11 equals negative 47. Here we're going to add 11 to both sides, and we have 2x squared equals, this is negative 36. At this point, we're going to divide both sides by 2, so x squared equals negative 18. Now we're going to take the square root of both sides, so x is going to equal plus or minus, we're going to pull the I out, right? Pull the I out. And the square root of 18 can be simplified, or can be, we have two factors in there, one that's a perfect square, which is 9, and then we have 2. So 18 can be divided into 9 times 2. So now we have the square root of negative 1, that is I, the square root of 9, that is 3, and you have the square root of 2 left over. Note that you have two solutions here, positive 3i square root of 2, negative 3i square root of 2. And you have two solutions here, positive 2i and negative 2i. Okay? Almost there, guys. Just stick with me for a little bit longer. All right, so what does it look like to graph something like this? Well, let's take a look. Something that has an imaginary solutions. Let's take a look. Example 8. If I have 4x squared excuse me 4x squared plus 20 equals 0. We're going to go ahead and solve this. We're going to subtract 20 from both sides. So 4x squared equals negative 20. Then we're going to divide both sides by 4. That means x squared equals negative 5. Then we're going to take the square root of both sides. So x equals plus or minus, we're going to separate this into the square root of -1 times the square root of 5. The square root of -1 we know is I, and then the square root of 5 we can't do anything about it. So these are the two solutions to that quadratic equation. Well, let's graph this. From what we know, the y-intercept is at 20. So let's say this is 5, 10, 15, 20. So the y-intercept is at 0, 20. Okay? And we can pick a couple of points here. We have 0, 20. We'll pick -1 and 1. If I plug in a 1 here, this is going to be 1 times 4, which is 4, plus 20 is 24. And you're going to get the same thing on the other side. So at 1 and at -1, you're going to be just a little bit higher. Yeah? This thing is definitely opening up. And the question is the following. Does this thing have any x-intercepts? Well, no. It's opening up. It's never going to cross the x-axis. All right? So we can say that quadratic functions without real numbers, real zeros. This is not a real zero. This is an imaginary zero. Okay, so quadratic functions without real zeros do not cross the x-axis. All right? There is no x-intercept. So remember I told you when we first started this whole thing that roots and zeros and solutions and x-intercepts all meant the same thing? Well, they do when it's real numbers. When it's imaginary numbers, you just remove the x-intercepts. This is still a 0. These are still the roots. These are zeros, roots, and these are solutions. But they are not x-intercepts. And that's because this is complex or imaginary. There's an imaginary part to it. If it was a real number, then it would be a solution, a 0, a root, and an x-intercept. It'd be crossing the x-axis. All right, guys. Well, that's it for today. And I will see you next time. Have a good evening. Bye.